sure that we get everything recorded. So tomorrow is Tuesday. The CIS department has a table right outside of the STEM building because this whole week is homecoming week. Yeah, whatever that means. I think it's the 70th anniversary of ARC. And I think the current college president wanted to kind of have more activities on the ground, bring people back on campus, and so on. So, there might be free food around. I cannot remember. You can look up, ARC Homecoming 2025, find out more. Okay. I think Saturday definitely has free food. I think there's a football game, and the first 800 participants, will get free food and a T-shirt. I cannot remember. Some stuff. Okay. All right. So, because somebody asked, I'm going to talk about your next exam then. Okay. Eventually we're gonna have to do it, huh? The homework? Oh, okay. I thought you were asking about the exam. You don't want to talk about that? Okay. Fine. All right. So what about the homework? Yeah, yeah. Uh-huh. All right. So maybe it is best to go back to the notes first because it is important to know where this is coming from. So this is too far. This is counting. This is the previous homework, which I disclosed the solution, right? So the CNF solution of this homework is already done. So basically, this whole assignment, the CNF homework assignment will give you the psi for resolution. All right. So now we go back to propositional logic. All right. So resolution is going to be the key to the homework assignment. Um, Basically, we want to do proof by contradiction, and the example is the key, okay? The overall strategy is here. So the overall strategy is basically giving you a psi. So this is just an example from the text, right? So in this case, the psi is different from your homework assignment, but it's same concept, yeah, exactly. So the first thing we did in the previous homework assignment was to turn psi into a CNF that is equivalent to the original expression. Um, so in this case, okay, this was the original psi, and then we use linear algebra, I mean, not linear, but Boolean algebra to turn it into a CNF. So are we good with that concept? Okay. So these two expressions, even though they look different and very different, but they mean exactly the same thing. They have exactly the same truth table. Okay, so that's one. So the next thing we want to do is to have a phi, uh, which is the which is the statement in question. Okay, the question is, does psi implies phi? Because if it does, then phi is a theorem with respect to psi. If not, then we just go like, okay, one does not imply the other. Are we good with that concept too? Let me say that one more time. If psi, which is this expression here, implies phi, which the original form is like this, if that implication is true, that so that is the same as saying phi is a theorem with respect to psi. Are we good so far? Then phi is a theorem, and typically we don't have to say with respect to psi, but that's more complete. Hmm. Are we good? The negation of t, the whole thing implies p in this particular example. So there are two examples involved. Okay, this is the first one. It's just something I pulled out of thin air to go like, okay, let's try this one and see if this is a theorem of with respect to psi. No, you do not have a choice. So you do not have a choice because I gave you your phi already in your homework. It looks nasty, but once you expand it, things will start to cancel out, and it's not quite as bad as it seems. Is that okay? Yep. Your psi is coming from the CNF assignment. So we did that already. Yep. Yeah. So correct. Yep. So in the assignment, it says, the next phase is to show whether a Boolean expression is a theorem of psi. So that psi is referring to the previous homework assignment. But I also, gave you guys the CNF of that particular psi, so you can use that. So you can use that as a starting point of this assignment. In fact, for those of you who have no idea what I'm talking about, hmm, it means you might need to watch the video. So in the solution, I actually explain it in a video, which I'm not going to play during the class. So if you have not watched the video of the solution of the CNF homework assignment, you might want to do that. We good? All right. So the phi is the proposed theorem. So this is a proposed theorem, which I do not know whether it is a theorem or not. So this is our phi. Okay. So the first step you need to do, okay, according to the instruction, okay, where is that? Not here. Okay, this one here. So according to this, what you need to do is to negate the theorem as a CNF. So if this is phi, then you have to first negate it, and then you convert that into a CNF, which is this one here. That is true. So the whole point of the negation is we are trying to use proof by contradiction. And proof by contradiction itself was explained a little bit earlier. Okay, so this is the concept of proof by contradiction is by introducing a conjunction between psi, which is everything that is known to be true. Typically it is just a conjunction of everything in iota. And then if you and it with the negation of the theorem, and this holds true, if this implication holds true, then this conjunction is going to be false. So that means, if I can somehow prove this conjunction is false, that proves this implication. Is that okay? So that's the whole premise. So there are three components. The first component is um, resolution. Okay, so resolution was some concept that we talked about even before this one. So if you go all the way back to the concept of resolution, it was kind of like way back. Okay, this is resolution. So this is resolution. Resolution is really just a mechanism where we can do kind of some kind of pattern matching and say, okay, if I have a conjunction of two disjunctions, where inside the disjunction, one disjunction has some kind of expression psi, the other disjunction has exactly the negation of that phi, of that psi, sorry, then we can this whole thing, this conjunction implies this disjunction here, and the magic trick is the resulting disjunction has one fewer term compared to the three terms that I need for this conjunction. In other words, every time you apply resolution, you are making the disjunctions simpler because you're losing terms every time you apply resolution. Yes. Mm-hmm. Oh, it's a or. This is a or. Yes. Yep. But the key is you can only use one expression at a time when you're performing resolution. So I can give you an example. I'm using Joplin for this purpose. So that means, if you have, um, let's say A or B, and then not B, or C, then this whole thing is going to imply, okay, right arrow, A or C. The B goes away. Is that okay? So let me give you a trickier example. So let's say you have this one. Okay, so you guys can focus on the right-hand side where it's formatted. So now the question is, well, first of all, can resolution happen? The answer is yes. The second question is, what does the result look like? So what do you think? You can only do one variable at a time. So that means you have to choose now. You cannot just go like, oh, A or B is on this side, and then not A or not B is on the other side. So the whole thing just resolves to false. That doesn't happen because what you can choose to use A for resolution, you can also choose to use B for resolution, but neither is going to get you anywhere useful. So let's just say that we choose to use A for resolution. So that means A and not A, they can't quote unquote cancel out, and then B is left over from the first disjunction, not B is left over from the second disjunction. So that means you only get true. Okay, the whole thing is just true, which in a conjunction is useless because true is the identity of conjunction. You can keep saying and true and true and true all day long, it doesn't change anything. So if you use B for resolution, it ends up kind of the same way because you're left over with A or not A, which is also just true. So that means in this case, you can perform resolution, it just doesn't help you. Because the idea of using resolution in this context is trying to get to false. So getting to true doesn't help at all. To this one, yeah, then you just have, yeah, exactly. You just pick up all the leftover. Yeah, yeah. So in this case, A is corresponding, this A over here is corresponding to the entire phi on this side, and then this C or D is corresponding to the entire row. Yeah, so rho itself can be a huge, gigantic disjunction on its own. Phi, I mean, in this case, psi can also be a huge, gigantic disjunction on its own. And resolution doesn't even require psi in this case to be exactly a single variable, but because of the way we converted everything to CNF, right? So because of that, we are only dealing with either a variable not negated or a variable that is negated, which simplify things a lot. All right. So are we doing okay so far? Kind of tying all the three pieces together. We have resolution, but in order to apply resolution, we need CNF. Okay. And then I show you guys how to use Boolean algebra to convert just any Boolean expression into a CNF. And then we introduce, proof by contradiction because resolution is getting rid of stuff. Okay, so eventually you get rid of everything and you get to false because the example that I used in class the other day was what if we have something like this? We have a or okay, we have not A or false, okay, because in any disjunction, or false doesn't do a single thing. Just like, adding a zero in a normal arithmetic expression, you can add zero to something all day long and nothing happens, right? So now you can have A or false. So using resolution, okay, this becomes false or false because that is the leftover from each side of the conjunction. Does it make sense? So now your leftover is just false, but false or false is just false. And in the process of using proof by contradiction, this is good news because that's exactly what we want to end up with. So we doing okay so far, with those three components and how they kind of interact with each other. We have once again resolution, which necessitates CNF. Okay, but once we have CNF, and resolution, then we have a really neat mechanical process to use proof by contradiction. So those three are all tied in together. Any questions about that statement? No? Okay. All right. So in the whole process, okay, we are also reducing the space to a finite space. Because if you have only five variables, the total number of possible disjunction is um, 3 to the power of 5, okay, which is a sizable number, but it's not infinite, right? So that means, when you're performing resolution, you are you're bound to end at some point. So you either end up with a zero, which means you have proven that psi implies phi, or you get to a point where you cannot generate any more new terms anymore, and yet you cannot get to false. So that means you are quote unquote at a dead end, which simply means that phi is not a theorem of psi. But other than that, there's nothing else you can say about it. Is that okay? Does that answer your questions? Okay, excellent. All right. So with that said, we are going to continue with our discussion on what was it again? Discrete probability. But we are still counting. We're still counting. Okay. So I think last week I made a statement of we're going to go through some pretty nasty, symbols and definitions. So that's exactly what we're going to do today. All right. So we'll go ahead and start with permutation. So section 6 talks about how do you come up with a permutation outcome set of experiments without replacement. So I'll give you an example, okay? Without any proof, I'll give you an example. And I'm going to use Joplin for this because it's just a whole lot easier to type here. So I want to show you what is the permutation outcome set of choosing. I'm just going to use two items, because otherwise it would take too long. So I will say choosing two items out of, in this case, is a particular set, and I can make the set. Let's say we have four items to begin with. Okay, I think this is an example that we have used quite a few times already. So now this is what I want to do. So now the question is, what do you mean by the permutation outcome set of choosing two items out of a set of A, B, C, D? So I'll just go ahead and show you exactly what it does have, and then we'll talk about how we can generate that test. So now we'll just look at the members, okay? So this outcome set has the following members. Okay. So the members are, yeah, they're pretty easy. You have AB, AC, AD, BA, BC, BD. I mean, I drew a tree last time, okay, so this is nothing, it's not new, okay, it's just that this time I just want to kind of present it like this, okay, as a list. C, D. And then finally we have the D's, okay, we have DA, DB, and DC. So how many do we have altogether? Okay, in other words, I'm just asking what is the cardinality of the permutation outcome set of choosing two out of four items. If I only worry about the cardinality, we already have the formula to do it, right? It's the permutation of 4 choose 2, which is 4 factorial divided by 2 factorial times 2 factorial. So that would be 4 factorial is 4 times 3 times 2 times 1. That's 24. 2 factorial is 2 times 1, which is just 2. So 24 divided by, oh, I take it back. It's not 2 factorial times 2 factorial for the denominator. It's just 2 factorial because we are looking at permutation. Okay. Apparently, you guys most people do not remember that discussion. So I'm going to say that. So the permutation of n choose m is the fraction of n factorial divided by n minus m, the whole thing factorial. We talked about this. Okay, so that means, if n is 4 and m is 2, then you have 4 factorial divided by 4 minus 2, the whole thing is 2 factorial. 4 factorial is 24, 2 factorial is 2, so the answer is 12. So now the question is, did we end up with 12 elements in the outcome set? Well, let's do some counting here. Okay. So what do you count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Are we good so far? So 1 will give you the cardinality. This will give you the cardinality, which is most of the time what we need to do probability calculation because you don't need the actual set. The other one will give you the actual set of members within that outcome set. So the question is, when do we want to know the actual outcome set? Well, okay. Do you guys do you know how to play okay, I'm trying to remember the name of the game. It's a board game and you hide a pattern from the other person. And then when the other person makes a guess, you have to say, okay, you have one that matches the color and the position, and you have one that matches just the color but not the position. What is the name of that game? Hmm? It's not Battleship. Um, it's a very common name. It's a board game. Okay, I can ask. Thanks to AI, it's easy to find it now, right? Okay. So what is the name of the board game in which one person hides a pattern and the other person tries to guess the pattern with some feedback? Woof. All right. Yep, Mastermind. It's an old one, yes. It's But that's exactly why we need to keep track of the outcome set. Because every time you get a score out of a guess, you can rule out certain permutations to be the actual answer. Now, in this case, it's not necessarily a permutation because you can actually have the same color. So it's not exactly a permutation, but that's the idea. Okay. Sometimes you have to track the actual membership of the outcome set because you are doing everything by elimination. Is that okay? All right. So get help with your toughest homework problems and more. Mm, not now. When I came up with these notes, the slides that you see here, I don't even use Wikipedia for the most part. I don't even look up. I just try. I try to derive everything on my own, and then I would check whether my solution is correct or not. All right. So that's basically where we are now. Okay, where we are at. Okay, so we're going to take a look at these equations here and see what they mean. So we'll take a look at the symbols. Okay, in the cases where the outcome sets of each trial TI is independent to other trials, the outcome set is just going to be easy. But since we're talking about without replacement, so that changes the rules a little bit. So let T represent the pool of choices originally presented. Furthermore, let omega I of T represent the outcome set of an experiment involving I trials, starting with T as the set of trial outcomes. It is easy to see why omega 0 of T is just a set consisting of an empty tuple. Okay, so we'll take a look at this case first, okay? Yeah, because what I consider to be easy to see may not be easy to see, okay? So first of all, what does it mean when I say omega 0 of t? What is that 0 representing? It means, oh, okay, We start off with a set T, which can be a set of A, B, C, D. When we have, think of T as a bag of marbles, okay? So this is the original bag of marbles. And then the zero is telling you, okay, conduct this experiment for me. Remove nothing from the bag, and I want to know what the possible outcomes are. Okay? Does everybody understand what I mean by that? You have a bag, okay? And in the bag there are a bunch of items, okay? And I'm asking you, okay, I want you to conduct this experiment, which is consisting of, okay, here's the table, okay? I want you to lay out the items in sequence, okay? The first item goes here, the second item goes here, the third item goes here, and so on, okay? So let me remove all the other things that is not part of the experiment. Okay, so now I'm asking you, don't remove nothing from the bag. So what is the possible configuration on the table? There's one configuration, which is the table is empty. There's nothing. So therefore, we have this set, which is, because the set consists every element or every member of this set represents one configuration of the table after performing the experiment. So we only have one possible configuration, which is an empty table. There's nothing on the table. Yep. Mm, well, we have to, okay, so you have to look at how many items we're supposed to remove from the bag. So in this case, it's zero. Okay, all right. So let's say, but are we clear on why this is always true, regardless of whether T is itself has what kind of membership we have in T? Does it make sense? So I can give you a huge bag with like 200 marbles, but if I'm asking you to remove nothing from the bag, you still have nothing on the table. Or I can give you an empty bag. It doesn't matter because you're not taking anything from the bag. The bag is empty, doesn't have any problem. We don't have a problem with that. Is that okay? All right. Um, so we can look at what if we are looking at omega 1, okay? So we'll take a look at omega 1 of t. So omega 1 of t means you're only allowed to remove one item from the bag and put it on the table. Is that okay? Because this one, if I put a 1 here as a subscript of omega, that I, okay, the subscript I of omega is representing the number of trials. I is the number of trials. Are we doing okay so far? Yep. No. Well, it's the same. The number of trials is the number of elements we are removing from the bag because each trial removes one item from the bag. Is that okay? So if we are looking at omega 1 of t, then the number of items in the bag will be the answer because I can only remove one item, right? So I can now say, okay, this is one of the items in the bag. Okay, since I can only remove one item, this is one configuration of the table. Okay. In another trial, okay, I can remove something else from the bag. This is another item from my bag. This is the second configuration of the table. Is that making any sense? Okay. So now I want to say, okay, but what if I'm looking at omega something and that, something, the number of trial is not zero, it's a non-zero. So as it turns out, we can do it recursively. So this equation here is a little bit harder to read, okay? So we'll try to read this, kind of like one step at a time, okay? So we are looking at um, I trials, and we have an original set of t, and we want to compute the outcome set of the entire experiment. Okay, let me say that one more time. We start off with t many items in the bag. we are supposed to remove items out of the bag, lay everything on the table, okay, where ordering is important, okay? And the way to compute this particular set is this formula over here. So are we understanding the purpose of the definition? We're trying to compute the outcome set of an experiment. The experiment involves starting off with a set T as the original items that are available to us, and we're supposed to remove I items out of the bag without replacement, and each configuration is a tuple because ordering is important. So are we good with what this is supposed to compute? Okay, so that relates to the earlier example. Okay, so if I were to, so in this case, um, one way we can look at this is these are all the members of omega 2 of this particular set. So are we relating everything? Okay, this example and also, what omega 2 of T actually means. Not so much how it is done, okay, just what it means. So are we good? Okay, all right. So the way it is computed is to use the big U notation here and blah, 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 blah. Okay. So what exactly is the big U notation? What do you think is the big U's notation here? In other words, what do you think is this notation is trying to tell us? All right. So if we are not understanding this, that's okay. It says for each element E in T, compute this whole thing. Whatever that thing turns out to be, union all of these things so that you make one gigantic union of the set. Yeah, go ahead. Huh? Oh, okay. Yeah, union. Yep, union. That's why we have a big U, because it's a union of all the things that we are generating for each element E of T. Is that okay? Hmm? Well, that's the detail, right? So right now we're just looking at an overview of whatever is inside the parentheses will give us a set. Okay, for each E, this will give us a set. Okay, we don't even care what they are. Okay, we just say, okay, whatever that set is, we're gonna have a gigantic union of all of those sets that are generated for each member E of T. Cartesian product. Yep, this is Cartesian product with omega I minus 1, and then you also have to remove element E from T, to become the set of available outcomes for the next trial. Okay, that's a mouthful. So are we good with this notation, or should we go back and kind of revisit the notation itself? It will give us all the permutations. Yes, correct. Yep, it will give us all the permutations, so the mechanism itself is the second thing that I need to explain, but I just want to explain the notation first. Okay, so I can give you an example. Okay, it is somewhat abstract, but also less abstract at the same time. Okay, so I can give you an example. So let's just say that we are looking at the big U. Okay, so I cannot even remember how to do the big U notation. So right click, show math as tag command. So it's a big cup. Okay. All right. So we're gonna say, big cup underscore um, E in, and this time I'll make it super concrete like ABC. Okay. So we have a definite set over here, and let's see whether it renders okay. Yep, it does render. And we are going to say some kind of function P, function F on E. Okay. So this is the notation. Okay, you can focus on the right hand side. This is the notation. The question is, what does that mean? Well, in this particular case, all it means is f of a union with f of b union with f of c. Are we doing okay so far with the notation? Okay. And you ask, what exactly is f? Okay, that is not the important part here. Okay, f is just some function that takes a, b, or c in this case as a parameter and it returns a set. And then all we are going to do with those three particular sets is to make a gigantic union out of those three, and we're done. Are we good so far? All right. So in the context of the definition, that we are looking at right now, it is just that f of e is, it looks like this. Yep. You mean this? I can actually put this side by side, always make it on top. You mean this part? Yeah, sure. So we'll take a snapshot of this, open the tiny little window with just it displayed. So this way we can always refer to that thing when we look at a much more complicated version of the same thing. So are we good so far? All right. Okay. So now the question is, what exactly is this f in the context of generating all the possible outcomes? Well, that f turns out to be something that looks like this. Okay. It makes use of the e over here, and it makes a little set out of it. It's called a singleton set, which means it has a single element. And then we have a Cartesian product, and then, oh, I was pointing to the wrong thing. Cartesian product with omega I minus 1. So that means the number of items I'm supposed to take out of the bag is one less than the original. But then the bag also has one fewer item. Okay, because we have to subtract the singleton the singleton set of E from T as the parameter to omega I minus 1. Okay, so that's kind of awfully complicated. So what we will do is we'll do this step by step. Okay. So what I'll do is I'm taking this equation and doing the same thing. I just want to display on the side so that we can refer to it. So we put it here, and then we switch back to Joplin. So this time we are going to work on a um, concrete case. Okay. So the concrete case is we are looking at omega subscript 2 of the set that we were just talking about, A, B, C, D. Okay, so that should, if we apply the techniques correctly, this should give us exactly the set or the membership that we looked at earlier, because it is exactly saying, okay, give me the outcome set of removing 2 items without replacement where ordering is important from a bag that originally has 4 items. Are we doing okay? Okay. Hmm? No, because I cannot remember what I just said. We are looking at the outcome set of removing 2 items out of 4 items, okay, from a bag of 4 items without replacement, and ordering is important. Yep. Yeah, the 12 items is not the outcome set, but they are the members of the outcome set. Yep. All right, so now what do we do? Well, according to the definition here, the first question we ask is I 0? Because if this I is 0, then we're all done. We know exactly what that would give us. It's the base case of recursion. But unfortunately, in this case, no, it's not 0. Okay, it's 2. So we now have to use the recursive definition, which is this one. So the recursive definition basically says, okay, we need to generate the 4 sets over here, which is f of a union f of b. So I'm going to define f, in this case, but give me a second here to express this first. F of c, and then we have f of d. Okay, that is what this notation is trying to say. Okay, for every element E in this particular set, for every element in A, B, C, D as a set, so that means A is one consideration, B is a consideration, C is a consideration, and D is a consideration. Use this complicated thingy, okay, and which I'm just going to call F here, okay, just so that it's easier to refer to it. Each one will give me a set. Okay, so what I'm going to do with the four sets that is going to be the result of this construct here, just make a big unit out of it. Are we good so far? Okay, so now we define F. Okay, because otherwise we go like, okay, what are we supposed to do with each one? So F in this case, okay, in this context here, is really just the expression of this part over here, except, instead of I, we have a concrete one. Instead of T, we also have a concrete one. So we'll make it as concrete as possible. So this is going to be E, which is still parameterized, Cartesian product with big omega. And this time I don't have to use I minus 1 because I know I is 2. So I minus 1 is just a 1. And then in each one, we know what T is, which is it really is just a set of A, B, C, D to begin with. And but the subtraction of the set of E, that part still has to be parameterized. So are we understanding how F of E is defined to be pretty much the same thing as what we see here, except T is more concrete over here, and I is known to be 2, so I minus 1 is just a 1. Are we doing okay so far with that? With how F of E is defined in this case? We good? Good, okay? All right. So now the question is, um, fine. Then what is F of A then? Okay, if you're so smart tech, and you can define F of E, then what is F of A? Well, F of A is exactly what you think it would be, okay, because we're just parameterizing, we're just using A here as an argument to E. E is a parameter, A is just one of the arguments that we need to supply to it. So it becomes A, which is an actual element, Cartesian product, okay, with omega 1 of, well, since we know E, parameter E is just element A, now we can just go like, okay, fine, this set is really just the original set, but without A in it. So it only has B, C, D in it. So are we doing okay so far? Okay, all I did was to say, okay, instead of using E as a general parameter, I'm using A as an argument to that parameter. And once we know A is a concrete element, then the whole thing becomes this. Are we good so far? All right. Hmm? Okay. Do we still have an outstanding question, or was it resolved? So the question was resolved. Okay. All right. All right, so now we have a little subproblem here, okay? Omega 1 of a set of BCD. So what are we going to do with, big omega 1 of BCD? The same logic, okay? So the first thing is, well, I wish that one was a 0. Because if it was a 0, I know the answer right away. What answer are we talking about? It is the base case that we mentioned up here. That's the base case, okay? Unfortunately, it's not the base case because it is non-zero. Okay, well, that means now we have to figure out what this thing is going to do. So what that thing is going to do is so this time we have to redefine F a little bit. We'll define G, okay? We'll define G of E to be, um, you know, the set E, the singleton set of E, Cartesian product with big omega of I minus 1, but because I is 1 this time, so that means we now have omega 0 of whatever t, but this time t is BCD already, and we have to subtract, the element e from it. So that is, so are we okay with how g of e is defined? So I choose f for one and I use g for the other one, but you can see they have a lot of resemblance. Are we good so far? Okay. So if this is how we define g, then we can kind of go back to the previous one and go like, oh, okay, we can just expand this whole thing so that it becomes, g of a union with g of b union with g of c. Is that okay? Because of the way we define g of e, which is the recursive version of, which is, this portion. So, once we define g of e to be like that, then we can rewrite f of a to be g of, oh, actually, I take it back. It's not, we cannot use a. So it's b, c, and d. That's my bad. Thank you. Okay. That was my bad. Okay. Because a is out. Okay. But we can, no, I take it back. Omega 1. Okay. So this is my bad. My bad. Okay. So this part is done already. But the next portion is omega, omega 1 of BCD is that part. Okay, now it makes a lot more sense. Okay, there we go. So are we good with this part? Omega 1 of the set BCD is G of B union with G of C union with G of D based on the original pattern of recursive definition. Yep, go. hmm Because I did the subtraction already. Because when you substitute parameter e with an actual element of a, I can actually do this subtraction. So that means we have a, b, c, d minus a in this case. So we only have b, c, and d left. hmm Are we still doing okay so far? Yep. So you're changing what to 4? So omega 4 instead of omega 2. So then it will take a lot more steps to get it down to 0. But then the outcome set is going to be the permutations of choosing 4 items out of a bag that actually has 4 items. So the resulting tuples would be there will be 4 factorial tuples or 24 tuples in that case. In this case, will end up with 12 tuples. hmm So are we still doing okay so far or not? Okay. So now we look at this part here and go like, okay, what is omega 0 of something? Ah, we know the answer to that question, right? So since we know the answer to that question, we go like, okay. Um, so we just, okay, I'm gonna copy and paste it because we know omega 0 of whatever is really just a set of the empty tuple. So we're gonna replace this whole thing and say, okay, this is a set of just the empty tuple. We good so far? All right. But that means, oh, the whole thing, I know the answer to this question already. Okay, this is an extra close paren here. So we know the answer to this question already because we just end up with so technically, okay, we end up with a two tuple that looks like this. Okay, so I will pause here first and then we'll make some adjustment. Does that make sense to you based on what we understand about the Cartesian product? Yep, go ahead. Scroll up. Oh, okay. Mhm. Okay, so does this equality make sense, this particular one? Okay, we have Okay, what is Cartesian product? We take one thing from the left-hand side, we take one thing from the right-hand side, and then we make a two tuple out of those two things, right? Well, in this case, it's pretty easy. There's only one thing on the left-hand side. There's only one thing on the right-hand side. So the only two tuple you can make out of that thing is just the E from the left-hand side and the empty tuple from the right-hand side. And then you make a tuple out of that whole thing. You have a nested tuple in this case. Yep, yep, yep. So we'll simplify this as much as we can before we plug it back in. Yep. Okay. So technically this is the correct answer, but in some context, such as the current context, we can now say instead of saying that this is a tuple of two items where the second item is an empty tuple, we'll flatten the whole thing to become a single tuple of just E in it. Are we doing okay so far? So I'm quote unquote collapsing all the empty tuples into nothing and make a single tuple out of the whole thing. Is that equality doing okay? So instead of saying we have a list or a tuple where we have something and the empty tuple as the second thing, we just say forget about the empty tuple. We just say that it is a tuple of one item. Is that okay? We're collapsing the structure. Are we good so far? It's kind of like looking at folders, right? So it's kind of like looking at a folder that has a file, and then the original folder also has an empty folder, but we only care about the files. So we just take out the empty folder and go like, okay, you are not important here. We just need to know what files are in the original folder, and that's what we end up with. Okay. All right. So if that is, if we understand that step, then we can plug that back into here. Okay. And then we can say, oh, okay, that seems pretty simple because G of B is really just the set with a single monotuple of B in it. And then that is unioned with something that looks about the same. And then this is also just unioned with something that looks almost the same, except it has D in it. Okay, so we'll focus on just this equality at this point, knowing that G of E simplifies to something like this. Are we accepting that G of B union with G of C union with G of D is really the union of these three rather simple singleton tuples? We good? Okay. So can we then say that, okay, it is just a set that is bigger with these three items in it. So give me a second to reformat this and this. Can we see how this union is really the same thing as this item here? Okay, all right. So now we have resolved this thing over here. So this means that we can now go back to this point and say, oh, okay. So we are looking at a set A that is now Cartesian product with um, a B in a tuple, C in a tuple, and then D in its own tuple. So are we doing okay so far? Plugging this back to over here. So I do apologize that I'm going back and forth a little bit, but we resolve things and then we plug it back in and so on. But are we doing okay? Yes? All right, cool. So now we look at this one here and go like, oh, do we know how to perform Cartesian product? Yeah. We take the one thing on this side and then pair it up with this thing over here, make it 1, 2, tuple. And then we pick up one thing from here and then pair it up with the other thing over here, make another two tuple out of it. And then we pick the only one thing on the left hand side and now finally pair it with the last item on the right hand side and make another two tuple out of it. Does it make sense? All right. So the end result of doing that, okay, is the following. So I'm just going to take out a bunch of stuff until we get to that point, okay? So that's basically where we ended up in the previous line. And now we go like, oh, okay. So we are having a two tuple where we have A and B, okay? That's our first two tuple. And then we have A and C, and then we have A and D. So we are focusing on this line over here. Are we doing okay so far with this? Okay. And then we look at this and we go like, we don't like, nested, tuples. So let's get rid of all the nestingness. Okay. And then we just go like, we will flatten everything, which means, we just remove all the nesting of the parentheses. So now f of A becomes AB, AC, AD. Are we doing okay? And that f of A goes back here. Are we doing okay? Yes. So what do you think is f of B? What if this is what f of A looks like? What do you think f of B is going to look like? So it would have BA, BC, BD as two tuples in it. F of C is going to look like CA, CB, CD in it. And then f of D is going to be DA, DB, DC. And then when you make a union out of those things, guess what you're going to end up with? The list that we just saw earlier. Is that okay? Yep. Go ahead. No, this is giving you the exact definition that you need to to def, to describe the outcome set of an experiment. So omega I of t is the description of the outcome set of removing I items out of a set T in a way that is without replacement, and ordering is important. Are we doing okay? Yep. I haven't decided yet on how I can ask questions about this. Well, okay, so I haven't decided yet how to ask a question about this. Yes, go ahead. Hmm? Scroll down, sure. I can share the document with you guys. Hmm. But it goes down, okay? It goes like down, and then we hit the end of the recursion when we get to the empty tuple set, and then we backtrack to backfill, all the items that we were working on. So this is it's that's why it's a recursive approach. It goes all the way down, and then we hit the base case, and then it returns, and then we have to hit f of b, and then we have to do the same thing all over again, and then backtracks, and then we go to f of c. It would do the whole thing again. But are we generally understanding the approach? Okay. So when you look at this, there are two ways to look at it. Okay, can I switch back to the lecture notes, or are you guys trying to copy something here? So we're good? Okay. So if we go back and look at these definitions, there are two definitions that are important. This is the base case. This is the recursive case. Now, when you look at the notation, it is kind of difficult to understand because I'm using mathematical notation, but everything in this definition, it can be done, it can be, you can translate it into code. Okay, so I can show you, approximately how we can translate this into code. And that will take a an editor. This one is good. Okay, so we'll use this one. Okay, so I'll just make an attempt, making this, into a JavaScript code. So we'll go ahead and say this is omega.js. Okay, that will give me the correct, syntax highlighting. So we're defining a function called omega, and it has two things. We have I as a parameter. We also have t as a parameter. Okay, so this is JavaScript. Okay, this is how you define a function. In other words, is a parameter, and t is also a parameter. Are we good so far? Okay. All right. So now we look at this and go like, okay, but what do we do to generate, the outcome set? So fortunately, in JavaScript, you can have iterators as a method. Okay, so that's a huge help. Okay, if you don't like, using iterators, you can use one of the for loops, and I can never remember which one I should be using. There's for in, and then there's also for of. Okay, so I have to look it up. JavaScript, huh? Yes, I will need to get there. Okay, but I need to get to the loop first. So for in versus for of. Okay. So for in is for property keys. So I guess it is going to be a for of in this case. But you can also use the iterator in a set. So in JavaScript, set is a built-in type, and with a set, you can also use any one of these methods, which means you have for each, which is super handy to have in this case. So if you go to for each inside the set, it is basically iterating through all the items in a set. Is that okay? Okay, so step by step. Okay, so I'm gonna go back. And where's my command prompt? Nope, not this one. Um, oh, this one here. Okay. All right, so I'm going all the way out. There we go. To the JavaScript interpreter. So we can just say node, okay? So this is one nice thing about JavaScript or most scripting language is in order for you to understand how it works, you can work with it interactively. You don't really need to write a whole program, compile it, and then run the program, and then you have to write another program to experiment. So what we can do is to say, okay, let's say, T is a set. The way you make a set is to say new set, and then in the parameters, you give it a list of members. Okay, so in this case, we can go like this is A, B, C, and D. Now in square brackets, we have a list, but this is one of the things you can do to create a set where A, B, C, and D are the members. Okay, there we go. And then you can use console.log to examine what is in T. Okay, so you can say, I think it's JSON.stringify T, and it tells you it is a set. It doesn't quite enumerate what is in the set. So now we can now say your T dot for each, and then you define a nameless function. Okay, so E is the parameter, and then whatever is on the right hand side of what looks like implication, which is not implication, is the body of the function. So now we can say console.log E. So this will basically just list all the members inside the set T, and we have A, B, C, D. Are we doing okay so far? How many people have programmed in JavaScript? We have some people. Okay. It's actually a really, really useful programming language to learn. Okay. Hmm? You don't like it? You can tell your boss that. Your boss would say, okay, we have a project here. This is going to be a JavaScript project, and you can tell your boss, I don't like it. It's a okay. Do you like Python better? You like C++? Well, C++ cannot do something like this. Not even close to something like this. Okay, okay, that's fine. That's fair. Okay, you don't have to like what you have to do. All right, so getting back here, so now we can say, okay, I need my own result. Okay, so result is going to be a gigantic set. So I already know this is going to be a new set, but it is empty to begin with. And I also know this is supposed to return result. This is the way I do things. I define a variable to capture all the answers, and then I also make sure that I return that variable at the end of a function. Okay, then I go back and say, okay, how do we figure out the result? So in this case, it is going to be something like this. Okay, so the first thing I want to ask is, am I kind of lucky that I is just 0 this time? Okay, if so, it's an easy case. If not, it's like case. Okay, so I'm using triple equal not because it is a typo, but because you really want to use triple equal whenever you think I really want to compare to 0. Okay, so there are a few ways to do the same thing. For those of you who know C, you could have said something like this, okay, where if we know that I is an integer, then not I in a context that expects a Boolean is really asking is I 0 or not, okay? But this is a scripting language, which means if I is a string, then if I is an empty string, that would be true too. If I is undefined, that would also be true. Okay, so there are many cases where not I will be true even when I is not even an integer to begin with. Yes. So if you use a double equal, it forces I to be now in an integer context. But I think, an empty string would still meet this requirement. It will still say it is true. But if you use triple equal, then an empty string cannot be coerced into an integer type anymore. And in that and in that case, when the program gets to this point, it's going to bomb out. So to confirm, we can always give it a try, right? So we can say what is not 0, it is true. What is not empty string, it is true. What is not undefined, it is also true. What about the negation of a string that is 0 in it? Okay, that one is false because it doesn't automatically convert it. Okay, so now we do the other comparison. We can now say, is that 0? It is true. But if you use triple equal, then it is false. So these are little things that you kind of have to learn when you start to program in JavaScript or most scripting language because it is typeless. Okay, I shouldn't say it's typeless. It is not strongly typed. Okay, it is weakly typed, which means the interpreter will try to be smart and say, well, you know what? In this context, I'm expecting a Boolean, but you gave me something that is not a Boolean. I will try my best to convert that thing into a Boolean context so that it can run. Okay, and that's why we see all of these things because 0 can be interpreted as false. Oh, there's one more. That one is obvious. That is also true, right? Okay, so I'm trying to get you guys to know something that is a little bit outside of the scope of this class. But if you are going to program in Python, in JavaScript, and most scripting languages, these things are important to know. Okay, there's a double equal, there's a triple equal. Double equal still wants to do the coercion. Triple equal says we have to match the type first. If the type matches, then we can talk. If the type doesn't even match, it's no, it's false right away. Yes. Yeah. If you use a double equal, then the empty string versus 0 would be the same. Hmm? All right. It likes that too. In fact, this explains one of the bugs in Canvas that I discovered when we first switched to Canvas. And I reported that bug, and I suspected it has something to do with something like this. And to date, it still has not been fixed. Say that one more time. Just zero versus false. Oh, that's for sure it's going to be true. You mean like, you mean this? Zero and then quote zero? Like that? It is also true because it does the automatic coercion. It looks at the type differences of the two sides, and then there's a way for it to kind of convert the types. So in this case, I'm not sure which way it is converting. Then it would be false because they don't even have the same type. Yep, yep, yeah. There are a lot of nuance, to programming in JavaScript that most people who program in C++ or Java would not get the first time. Yeah, similar to Python. Yep, Python is similar. If you compare type checking, Java is the strictest. Okay, so Java would not even let you use an integer in a context where Boolean is expected without the actual explicit conversion. C++ would let you do it. Yep. Yeah, yep, because the virtual machine is available on all major platforms. Nope, because the libraries are also expressed in bytecode. As long as you can get a JVM or Java Virtual Machine to run on a platform, it will run the bytecode from anywhere. Yep. All right. So now getting back to, I just wanted to make a point here, okay, which I did. So we go back to this code here. So now we can go like, oh, okay, result is pretty easy. Okay, we just have to add a member, which is an empty tuple, into the set. So the way you do it is result dot add because it actually know what result is. It's a set. So you use add to add an element. In this case, the element would be just an empty tuple, and we're done with this base case. So what about the other case, which is not the base case, which means I is at least one, or I probably should have checked whether it's at least one or not, but we'll just assume it is. Okay, so in this case, the result is going to be the union of all the things, depending on omega, right? So now we have, and also the Cartesian product. So looking at the equation over here, so now what we need to do is to say for each, okay? So this is going to be t dot for each, okay? So this is where I need to kind of break up things inside the whole thing. So now we look at E, okay? So what is inside the braces over here would be the same stuff that we have to do over here. Okay. So now we say, so we say for let temp, okay, equal to the following, okay, which is trying to capture this whole thing here. Now, there's no actual Cartesian product for the set type, unfortunately, so we'll just have to kind of imagine that there's one, okay? So we will say that, temp, okay, we create the variable first, and then okay, we can do something like this, okay? We can say new set, okay? And the only thing in the set, the only element, we can initialize it with E itself. So this item here is essentially this item over here. So we'll assume that a set has a Cartesian method. So we'll say Cartesian product with whatever is on the other side. So this is where the recursive call comes in. So the recursive call is basically the same thing as calling omega again, okay, with two parameters. The first parameter is going to be I minus 1. So this is I where I minus 1 goes. And then the second one is we can imagine that T or the set type has a minus, has a subtraction. So now we say T minus or T subtract. And then what we're subtracting from it would be the singleton set of E itself. So this would be subtracting new set with just E in it. So that would be, and then after the temp is computed, then we are going to union that with the result. So the union, so result is the running union, so to speak, of all the temp results. So this would be assuming Cartesian is an actual method and assuming union is also a method. This would be the code corresponding to the rather cryptic recursive definition over here. Is that okay? So you can see the code is not really that complicated, right? It is, I mean, you do need the set type, okay? And the set needs to support your union and also Cartesian product. But other than that, this is basically what the code translates to in JavaScript. So since some of you has expressed that you don't like JavaScript and you prefer some other programming languages, so my challenge is do this in your favorite programming language. Because I can guarantee you in C++, this is not easy. Okay, the code that you end up with is going to be quite ugly. Hmm? Subtract? Well, if subtract does not come with the original set method, you can always make it. So I have my own set type. It's called your text set, and it has all of these operators already defined. So once I include my library, this would actually be almost exactly this code. It would just work. Do you guys want to take a look at the code? Sort of? Okay. Meet my little friend. Okay. Teachers, exams, CISP 440, and choose any semester. This is my library, and there's a set text set. There you go. So this is my class definition, and it has all the other methods. So it has union already defined, which is really just a call to one of the other functions. It has add also defined, intersection, making a singleton, checking for membership, and then here's subtract. So when you look at set subtract itself, it's not really that big of a function. I mean, that's all it does. Okay, it goes through everything and make sure that things that are in S would not be in the result. That's basically the way it does it. The biggest problem that I had was the comparison of set is not the way that I needed. It doesn't do a structural comparison. It just says, okay, do these two things have the same reference? So when you have two set objects, they actually have the same membership, but they are created separately and therefore they have different references. They will be considered as two different things. It would not be considered the same thing. So that was my main challenge is I have to actually write the code to recursively traverse into complex objects and then do the comparison accordingly when we are dealing with either tuples or sets or stuff like that. So anyway, all right. So are there any questions? No questions? Any questions about the at least pseudocode that is actually really close to the actual code? In other words, looking at this picture, this code, and this definition, nope, not that one, the other one. Where's the other one? Mm, okay, so the other one is here somewhere. There we go. So looking at this definition and the base case, and looking at the code that I was just showing, are we seeing the correspondence? Okay, all right. Well, that pretty much concludes today's lecture. I think on Wednesday we can talk about exam 2, and I can send you the file that I was looking at earlier. So this way you guys can read it a little bit earlier, before the test, before the class, and then I'll talk about the answers. All right. I'll see you all on Wednesday. And by the way, tomorrow is the second day of homecoming week. So the CIS department, mostly me, is going to have a table, outside the STEM building with displays and stuff like that. I actually made an I made a jam in Gemini to help people decide whether computer science is a good fit for their major or not. Obviously, it is too late for you guys, so you don't have to show up if you don't want to. Well, okay, all things considered, unless you think you only have 2 years of life left, it's not too late to switch. Yes. Yep. hmm hmm So now you have to be careful with that not. Yes. Yes. So a negation of Q or T, I'm just using this as an example, is not, it is not Q or not T. You have to apply the Morgan's law. So with this one, because the negation applies to the or over here, you have to use the Morgan's law. Yep, yep. Yeah, well, not too bad. It's once you have a CNF. So once you turn not phi into its own CNF, then you combine that CNF with the psi CNF, and then you keep doing the resolution until you run out, until you cannot do anything, or until you get to a zero. I can tell you it's a zero. The question is, how do you get there? Yep. hmm